What if the force that working on the system is not constant? Before we said that work is equal to force that dot s in terms of vector, right? Or F s cos theta. In this case, your force is constant. However, in some scenarios, force may not constant. It can be vary with the position, or it can be vary with the times. So how can you do calculation on part of that? First of all, you can look after individual event of the force. Here, as you look after the force and position relation here, you can see force is changing through the displacement. So if you square in a small area and sum it up, what you have seen here, this bar is like you have fx dx is your delta work in some small region. If you would like to have the whole area under the curve of x, fx and x, so that you can do some integration. So integration is what you do some continuous combination. So you combine all these area together to get the final work on the system, which is can be done not only in one dimension, it can be also in 3 dimensions. But this example is in 1D when fx is changing along x position. So the work that you can find is the area under the fx curve, which is this part that what I said already. The reason that I put the sigma f over here to state about the net force. So the net force you consider on that only. For example, if this box has been acted by this force and this force and this force, but mostly object moving along this direction, so the net force is this term, not this and this part. That's why you need to consider about net force. Maybe at individual event and you sum it up under the integration of the small region. You will learn more about this in the example. This is an example that the particle moving in the term of this relation. So from the 0 position to 4 position, this particle was acted by some force with the constant force between A and B. And after 4 meters, you can see the forces varies, right? And df by dx in this case is getting lower. So this is how you have the system that the force is constant and the force is not constant. So how can you find the work out of this system, that force done to this system on some particle? So this is done on particle by force. The work is the area under the fxx curve. Right, so that if you would like to find the total work that's done by the force, so that you can find the area underneath it. So what you have the area from A to B, right, which is the rectangular area, and you plus with another area which is like right triangle from B to C. So what the area of the rectangular one is width and height, right? Width and height. How about this one is 1/2 and width, another width and a height. So let's replace the value in. So the width is 4 meters and the height is 5 Newton. How about this one? The width is 2 meters and the height is 5 newtons. So finally, you're gonna get 25 joule or Newton meter as a total work from A to C. This is what you can use the knowledge of the varied force in relation of Fx and X curve. Underneath is your work, which is this the total work from X equal to 0 to 6 meter. As I stated, like work that done by the varying force, one of the key example is what happened in spring. So when you try to pull the spring off, when the spring is like thing that keep resist to the extension, when you try to extend out the length of spring, there's going to be increasing force pulling it back. We call that type of force as a restoring force, because it's trying to restore the position to their equilibrium position. The position that the spring not pull it off, we call this is as a equilibrium point. Or position. Since this position is like all the energy restored here, if you pull it, you increase the force that try to pull it back. So the direction of the restoring force is opposite to the displacement or the extension that you try to pull it away. So that means now you try to pull it away to this direction, so the force is going backward. You have the minus sign in front of it, and this restoring force equal to minus kx. The force is vector, so remember, calculate anything like this as a vector. And think about the varying force. So rather than we have work equal to Fs, we have to do some integration of the net force, which is in this term, the net force is equal to minus kx. So if we do integration on x1 to x2, in this part we will have the change of the some kind like elastic energy potential. This is elastic potential in the spring. I will explain about this term later when we would like to look into the potential and kinetic energies. So let you know that in the varying force, one of the example is what happened in the spring. This is an example of how you find the work that done on the spring in different scenarios. So in this case, this was used for quantifying the spring, and the task that you have to do is what is the spring constant. The spring constant is k, right? Because you know F equal to minus kx. K is the spring constant and x is the extension length. The reason I'm not explaining much in the previous slide, because I would like to explore through the problem, and I will identify individual part of the interesting spring to you, and how you can understand about the work that link to the spring in terms of if you would like to do some extension and how work that is done to this system. So if spring is stretched 2 centimeter by a suspended object, that means this is the original position before this mat loading, and after the mat load, this keep extension and turn to a new equilibrium. The reason this spring has been pulled because the mg from the mass, and then it take a rest. So in this case, what you have seen, we look after into different condition, but the clear idea is looking at the condition number 2. So what we happen here, this is also at equilibrium. So that the sigma Fy equal to 0. That means you got the downward is a mg, and the restoring force is pointing upward. So you will have the mg equal to kd. With this case, you will roughly determine the spring constant as k equal to mg over d. So let's replace all the information that you know. So firstly, we determine the spring as a massless spring for this condition. So we simplify that the mass only comes from the loading mass, or the mg here. So suspended object is 0.55 kilogram, so 0.55, and g is 9.8, right? I will assume here that g equal to 9.8 meter per second square, and the d is the extension or the displacement, right? Which is in this case is extended for 2 centimeter. So after doing the calculation, you will find the spring constant is equal to 2.7 multiply 10 to the 2. What the unit of the spring constant? Since you know the F equal to kx, if you said about the restoring force, it's minus kx because it's point in the opposite direction of the displacement, and the k is the F over x. If you would like to consider only the magnitude of it, so you can just ignore the minus sign. So the force is unit in Newton, and the x is the length, so unit is meter. So the unit of the k or spring constant is Newton per meter. What is the spring constant? Spring constant tell you about the stiffness of spring, how the spring resists to the force that you try to pull it off. If you have the higher quantities of the spring constant, you need more force to use for extend the spring displacement. Or if you like to contract, not only you extend it, if you like to contract the spring from the equilibrium position, you need more force to contract them as well. Contract or compress is what I try to explain here. Next is how much work is done by a spring. So now look after the spring that done to the system on the object. Now work of spring done on the object at its stretch to this distance. So you would like to quantify the work that done by spring. So as the work is equal to integrate of sigma F dx, which is in this case maybe sorry, dy, right? And F is with the y extension, so it integrate minus ky dy, because this direction is y, right? And moving this direction maybe with minus, and upward direction is plus sign. So if it's onward like this, it's gonna flip anyway. So I ignore the sign, but I keep with this kind of information as the minus relative to the work that done by the force from the spring. So think about the thing is different from here. So this is the force that you try to pull it. It's not pulled back by the spring. But in this case, because of minus ky, this force is due to the spring itself. Try to pull itself back to the equilibrium position. That's why I put the minus sign here. But if you said about the force that is done by some people on the object, so this sign gonna be different. F here that you apply to the system should be ky. So this is difference. So the work that someone work on this system and the system work on its own is different. You have the same magnitude, but the size is different. Okay, let's go back to this part. So in this case, object, which is in this case is the spring, has been extended from 0 to y. So we will do integration on this part. So it's minus ky integrate dy this term. So I'll remove the thing that not involved outside. So integrate y dy from 0 to y. When you do some integration, you're gonna get the value of the y squared up over 2, right? And then you put the limit into it, 0 to y. So what you're gonna get here, you got minus k over 2 of y square minus 0 square. So the work that is done by spring on the object through this d distance, which is this y finally equal to d. So you're gonna replace minus k over 2 d square is equal to minus k is what you have found, 2 plus 2.7 10 to 2 over 2 and d square, which is stretch distance is 2 centimeter. So finally I will write down the work here after the calculation is equal to minus 5.4 10 to the minus 2 joule. This is quite important. The minus sign here tell that this is what is done by the spring, not by the people who try to pull the object away to have a distance d. Because if you sub the integration this part to ky, you no longer have this minus sign. So that let I remind you again, every time when you look into this type of the system, you have to identify on which system are you looking after and whom working on this work. And work is done by whom? That is what I try to say. By the spring on what things that this has been done. So let's go through the example and revise it, and you will have the big picture of how you deal with the work and energy. So as I said about the work that we know is equal to the change of the US, right? But if you said the work is done by the spring, which is I call the internal system. Internal system. You will get U1 minus U2, right? Which is this is minus delta U. But if the work is done by external or maybe with the applied force, you will have this rather than U1 minus 2, you will have U2 minus U1. So it depends on what are you looking after. And the U here is the elastic potential, which is equal to 1 over 2 kx squared. We derived this in the previous example. So this is how we understand about the picture of elastic potential, and then we can use for calculate the work and energy for the following section. So now let's sum up. If we have two different frame of view, This is the spring, right? This is the mass. If you say about the spring that does have the work that done by the external force. This is the thing that we call external force, and this is the thing that we call the internal force, which is the restoring force. Right? This thing is different. The only thing that's different is the minus sign over here. So if I said about this case, I'll integrate with the force that equal to minus kx. This is the work is done by spring on the objects, which is this box. Maybe I will write like a box or object M. So if I integrate with the sigma F app here, this part, that is how you get this one equal to kx. So you will get the work is done by the external force on the object M as well. So with different size, you got the work that done by the external force. This is work is done by the spring itself. This is like elastic or internal force.